Welcome to EPG Pathshala. I'm Professor Sharada Srinivasan, Dean of the School of Humanities at the National Institute of Advanced Studies in Bengaluru, and I will be taking you through the course for Indian culture and the paper on art and architecture, and the module that I will be discussing today is on history of metals and alloys. The significance of the topic is that to understand culture and art, we also need to understand the ways in which objects have been manufactured, the material culture associated with the objects, the processes involved, and the history of technology, since all materials have a technological underpinning. And along with that, we also gain insights into the other aspects which are important to us as historians and art historians, the aspects of the dynastic chronology, the patrons who made them, and the styles and such like. So in this module on history of metals and alloys, we will be looking into the history and usage of metals and alloys in terms of understanding their contributions to the march of civilization. And we will also be looking in particular at the history of metals and alloys in the Indian subcontinent and the trajectory of metals usage. And this is also an important aspect in terms of the discipline of archaeological science, and the study of metallurgical heritage is also known as archaeometallurgy, and archaeomaterials research forms an important subdiscipline in terms of the study of archaeology. So the module in summary aims to provide an introduction to the major metals and alloys which were used in antiquity and to highlight the Indian contributions and the significance to the history of art and history of technology. Early society's fascination with metals stemmed out of a demand for a range of utilitarian artifacts such as weapons and tools, while there was also a place for decorative and ritual and symbolic artifacts. The usage of metals going back to early prehistory and the production of metals and alloys has greatly contributed to laying the foundations of science and technology. And the trajectory of the extraction and production of metals and alloys is a very important aspect of the story of civilization. Whereas modern metallurgy has seen an exponential growth since the Industrial Revolution, it is interesting that already several important innovations and inventions have their seeds in ancient or traditional practices. We will now be discussing the antiquity of the use of various metals. Metals were extracted and utilized in the past in several stages, progressing from the use of native metal, i.e. those metals which were easily found in the native state, to those which were found in combination as ores, and there too it was those which could be easily smelted from the ores which were first identified, and then those which were more difficult to extract or smelt were discovered later. When we talk of smelting, we are talking about the process of the reduction of the ore to the metallic state using pyrometallurgical techniques. The commonly used metals in antiquity include gold, silver, copper, iron, tin, lead, zinc, and also mercury. The Indian subcontinent, like other civilizations, has made major contributions to the early development and use of such metals. We will first start with the noble metals of gold and silver. Gold and silver, being noble metals, are found in the native state, and since they were rather soft and ductile and had a bright luster, they were uncovered to make jewelry and also hammered into sheet metal due to the great ductility. Gold was uncovered in the alluvial form as nuggets from streams, whereby the hard rock gold was washed down the alluvial streams, and these sort of nuggets were retrieved from riverbeds. The repoussé technique of hammering in relief was used to make elegant gold vessels going back to Mesopotamia in 2500 BCE. The mask of the pharaoh Tutankhamun from Egypt is another celebrated example. In the Indus Valley sites, gold and silver ornaments were found at sites such as Mohenjo-daro going back to 3000 BC and Kunal, which included several sheet-hammered artifacts such as gold headbands and silver anklets and fish motifs made by the repoussé technique. It's interesting that in the South American civilizations, although they never progressed at all to the use of iron, they used gold in very spectacular ways for a range of artifacts. The Incas, the Aztecs, and the Muiscas in Colombia all used a range of artifacts in noble metals. And some of the most interesting artifacts of gold are the unique Tambaga alloys, which are gold, copper, silver alloys of about 40% gold, which were used for making castings and sheet metals. It's interesting that when we come to gold and silver extraction, some of the earliest evidence for the deepest old gold mines in the world probably come from India, from the Musky region of Karnataka, where carbon dates from the mid-1st millennium BCE have been uncovered from very deep mines. So these were hard rock mines where the gold was uncovered from the quartz veins. And then these were crushed down using mulaccas, and you see numerous mulacca fragments as well in the region of the Hatti Musky area where the old gold workings are still found. Gold would have also been collected by panning the alluvial sands from placer deposits. The Aravalli region in northwest India is also one of the very early major silver producing regions from about the 1st millennium BCE, along with other sites such as Lavrion in Greece and the Roman mines of Rio Tinto in Spain. And silver is also extracted by the process of cupellation in earlier times. We now come to the usage of copper and extraction. It appears that native copper, or copper in the unalloyed metallic state, was the first metal used by man going back to ancient Turkey and Mesopotamia about the 7th millennium BCE. It is also interesting that native copper was abundantly available in the Great Lakes region of North America, and the North American Indians used the native copper to make weapons and implements solely by hammering and annealing, so that they never needed to attempt casting and smelting. Early evidence for smelting copper comes from the Middle East from about the 4th to 3rd millennium BCE from parts of Israel, Jordan, and Egypt, where copper oxide ores such as green malachite were smelted at temperatures of around 1200 centigrade. Arsenical copper was also used in Mesopotamia prior to the use of tin bronze, of which the most famous and extraordinary examples are the bronze bulls of the 3rd millennium BCE, where the enrichment of arsenic at the surface was found to give a shiny coating. Early copper smelting is reported from the pre-Indus Valley sites of Baluchistan in northwestern India, of the part of the subcontinent close to the Iranian border of about 6th millennium BCE. There is also evidence for smelting furnaces from the Harappan civilizations and extensive evidence for the ancient mining of copper ores from the Khetri region of Rajasthan, dating to about the 3rd to 2nd millennium BCE. Tin is another very important metal in antiquity, which was alloyed to copper to make bronze to typically harden the soft copper, and then it was used to make tools and weapons. Tin ore occurs also as alluvial deposits or stream deposits, and it also occurs as ore bodies. Some of the extensive regions which had tin mines include Cornwall in Britain, while Southeast Asia and Thailand also have very large alluvial tin deposits. So prior to the use of iron, it was tin that was alloyed to copper to get harder bronze for weapons in the Bronze Age cultures of the world. And Turkey is also known to have ancient tin mines dating back to the 3rd millennium BCE. Amongst the earliest castings in the world is a well-executed statue of the dancing girl from Mohenjo-daro from the Indus Valley. While beautiful bronzes are also known from ancient Egypt, such as the famous cat, which is thought to have been executed by the lost wax technique. In China, very impressive ceremonial vessels were cast into clay molds by the late 2nd millennium BCE to early 1st millennium BCE. The Greek bronze figurines of the mid to late 1st millennium BCE are well known, such as the rider with horse uncovered from a shipwreck near Artemision circa 150 AD. When we come to the medieval period, some of the most beautiful and well-executed statuary bronze casting in the world are the famous icons of the Chola period from the Thanjavur area of South India from about the 10th century, which depicted images such as the celebrated Nataraja of the dance of the Hindu god Shiva. South Indian bronzes were often made by the solid casting process, whereas Northern Indian and Southeast Asian bronzes were often also hollow cast, which also followed the Hellenistic technique of making bronzes by the hollow casting technique, which we will discuss in another module. So when we speak of bronze, it is interesting that, as I mentioned, the addition of tin to copper hardens bronze. However, if we keep adding too much of tin, then the bronze also becomes very brittle with higher amounts of tin. And that is also why, for making cast artifacts of bronze, a certain amount of lead was also alloyed to the bronze to make it more castable. However, when we keep adding tin, which goes beyond the solid solution of tin in copper, which is around 15% tin, as I said, bronze becomes very brittle. And normally, the as cast artifacts that we have been talking about, like the statuary images and so on, those don't have tin which goes much beyond 15%, staying within the alpha solid solution. However, it is quite interesting that particularly in the Indian subcontinent, the ancient artisans had discovered ways to use bronzes of a higher amount of tin to specifically identify and isolate certain properties which were useful to them for making specific objects. A very brilliant example of this is the metal mirrors which are made even today in the village of Aranmula in Kerala. Here, a novel method of making mirrors survives, whereby a specular bronze alloy is used with around 33% tin, which is deliberately chosen because it has a very silvery white color due to the presence of the delta phase of bronze, which forms around 32.6% tin. It's an intermetallic compound. And this alloy is also very hard and it takes a very good polish, so that the reflectivity is almost as good as a glass mirror, even better in fact. And we also see that there is the novel use of another type of alloy with a high amount of tin, the high tin beta bronze, which is a very specific alloy with a tin composition of around 23% tin. And the idea is that at this particular composition of bronze of 23% tin, bronze becomes very forgeable at high temperatures. It can be worked considerably. And then when this particular alloy is quenched after forging, the retention of the plastic beta phase takes place. And the retention of this plastic beta phase contributes to musical properties to the alloy. And when it's polished, it takes on a very brilliant golden luster. So it seems that already in very early antiquity, such as in the Iron Age megalithic cairns of the Nilgiris and the Iron Age burials of Adichanallur in Tamil Nadu, you find these very extensively hot forged and quenched beta bronze vessels of around 23% tin, which are forged to extraordinary thinnesses, and they represent a very skilled metallurgical tradition, and it points to the fact that bronze metallurgy in ancient India was much more skilled than we understood at present. In some of the traditional workshops such as Aranmula, you still see the manufacture of the making of these skilled metal mirrors, which were made of a specular alloy with 33% tin with the best possible reflectance. And as you can see from the microstructure, you can see that it has a very silvery white color due to the prevalence and the optimization of the presence of the delta phase of bronze. And though this alloy is very brittle, the whole casting process and polishing is geared up to optimize the presence of the delta bronze alloy to get the best possible mirror. We now come to the saga of zinc metal production, which is another very remarkable technology which the Indian subcontinent made seminal contributions to. In fact, the earliest firm evidence for the production of metallic zinc is from India. Of the various metals used in antiquity, zinc is one of the most difficult to smelt or to extract because of the fact that zinc volatilizes at about the same temperature of around 1000 degrees that is actually needed to smelt the zinc ore. Evidence suggests that in India there is unique and extensive pre-industrial remains for the production of metallic zinc in the Zawar area of Rajasthan. In fact, Zawar has been awarded the International ASM Landmark in 1988 for the remains of the zinc distillation furnaces. To describe this Indian method of zinc metal production, an ingenious method was devised of downward distillation of the zinc vapor formed after smelting the zinc ore. This was achieved by using specially designed retorts with condensers and furnaces or koshtis that enabled the smelted zinc vapor to be drastically cooled down to get a melt that could solidify to zinc metal. It's also very interesting that the 12th century text, the Sanskrit text of the Rasa Ratna Samuchaya, describes this method of zinc production. And in fact, at Zawar, you can still see the remains of the koshti furnaces with the retorts, which the Rasaratna Samuchaya in fact describes as being aubergine shaped. And the condensers have a stem and the portion in which the ore is packed, and then the downward distillation into the bottom of the furnace takes place. And in fact, the furnace is heated on top above the perforated grill through which the retort goes down to the bottom of the furnace. So it is a very ingenious way of designing a furnace which brought about this efficient process of downward distillation of the zinc vapor. And rasa here refers to the zinc vapor. It's also very interesting that the production of metallic zinc was virtually unknown in Europe until William Champion first established commercial and industrial zinc smelting operations in Bristol in the 1740s. And in fact, it appears that William Champion was quite a lot influenced by the process that he would have seen in the Zawar area. We now come to another very interesting innovation in terms of the metallurgy of zinc, the use of the remarkable Bidri ware alloy, which was a highly elegant ware which consisted of an inlaid high zinc alloy with about 8% copper. And the use of the Bidri ware flourished under the Muslim rulers of the Bidar province, now in Karnataka, from about the 14th century. And a very important aspect of the Bidri ware is the patination, which was obtained by immersing the high zinc alloy in a particular mix of salts, and then the final inlaying was done with silver, and several impressive vessels are made of Bidri ware with geometric and floral inlaid metal work. The advent of iron was, of course, a very important development in terms of the early development of metallurgy, and which changed the course of humankind, because the copper and bronze tools, when they were replaced by iron tools, it was much more efficient in terms of agricultural processes and also for expansion of empires and warfare and such like. It is interesting that iron occurs in the native metal state as meteoric iron, and meteoric iron has also been used by various civilizations. The North American Indians used meteoric iron to make weapons, and it is also thought that some of the very early iron used in Egypt was of meteoric origin. The production of bloomery iron is traceable to about 1200 BCE. Since iron has a very high melting point of about 1550 degrees, it was commonly produced in the Old World by reducing the ore to the metal in the solid state to produce bloomery iron, and the use of shaft furnaces was made to produce the iron bloom. It has been thought that the Hittite kingdom was one of the major early iron producing centers by the mid-2nd millennium BC, and was thought to have had an early monopoly of iron production from where it spread to the Mediterranean. However, we should also note that there seems to be interesting and early evidence for the use of iron in India as well, at least by the latter part of the 1st millennium BCE, with evidence from the Gangetic Valley and about the 2nd millennium, and also from the South Indian or Deccan megaliths, where in particularly the finds of iron became very widespread to the point that they are known quite often as Iron Age complexes. A most spectacular testimony to the skills of early Indian iron workers is the Delhi Iron Pillar, which stands in the Mehrauli complex in New Delhi. The forging of wrought iron seems to have reached its zenith in India in the 1st millennium AD. The largest massive iron forging is the famous iron pillar at New Delhi, which is dated by inscription to the Gupta period of the 3rd century AD and towers at a height of over 7 meters with a weight of about 6 tons. The pillar is believed to have been made by forging together a series of disc-shaped iron blooms. Apart from the dimensions, another remarkable aspect of the iron pillar, for which it attracted the attention of early metallurgists going back to Robert Hadfield, the remarkable aspect has been the absence or relative absence of corrosion, which has been linked to the fact that the wrought iron was of a very high purity, and it is also thought that it had a significant content or trace of phosphorus, which contributed to the corrosion resistance along with the efficient distribution of slag in the process of forging. And the iron pillar has also been designated as an ASM International Landmark. It's also very interesting that the Indians had gained very early mastery in the making of high-grade steel. India has been reputed for its iron and steel since Greek and Roman times, with the earliest reported finds of high carbon steels in the world coming from these regions. Woods is the anglicized version of ukku in the languages of the states of Karnataka, Tamil Nadu and Andhra Pradesh, denoting steel, which several European travelers observed was being made by crucible refining processes. And Indian wood steel is thought to have been some of the best grade of steel that was known in antiquity. And you were looking at a specimen of woods which was now in the Science Museum in London. The term woods may derive from the old Tamil word ukku or urukku, which refers to the process of melting, and it also finds usage in Tamil Sangam texts. Literary accounts suggest that steel from the southern part of the Indian subcontinent was exported to Europe, China, the Arab world, and the Middle East. According to the early accounts of Quintius Curtius, he wrote that in the 1st century AD, during the campaign of Alexander, the Macedonian conqueror in the Indus region, He is said to have been presented with 100 talents of bright iron or ferrum candidum. As indicated in the accounts of the 17th century traveller Tavernier, tens of thousands of shipments of wood steel were sent from the kingdom of Golconda in modern Telangana to Persia and West Asia to make the fabled Damascus blades. The Damascus steel blade, believed to have been forged of Indian wood steel of a high carbon content of 1.5 to 2%, was reputed for its cutting edge. Henry Yule mentions the references made by Marco Polo, the Venetian traveller. The 12th century Arab Edrisi also mentioned that the Indians excelled in the making of steel, variously referred to as Al-Hindi, Ondanik, and Hinduani. The fame of the wood steel also derived from the fact that it was the raw material used to forge the Damascus blades. And according to accounts, the best of the Damascus blades were forged in places in West Asia, such as Damascus. The typical damask or watered silk pattern was obtained by etching a forged woods ingot to get alternating patterns of pearlite and cementite, which related to the metallic structure of the high carbon wood steel. This pattern enormously intrigued 19th century European metallurgists, and the Damascus blade was one of the first items to have been studied under the microscope. When we talk of wrought iron, we are referring to iron with a very low content of carbon of less than about 0.04% carbon. And when we talk of wood steel, we are referring to a high carbon content of 1.5 to 2% carbon. And the skill lay in the fact that to make this steel, wrought iron had to be carburized in crucibles at very high firing cycles at very high temperatures, going up to about 1300 degrees centigrade under highly reducing conditions, so that it was a very skilled technology that had to be perfected to make the ingots of high carbon steel. It is also very interesting that the attempts to study and characterize the Damascus blade, which had a very interesting macrostructure of visible layers of cementite and pearlite, actually led to several innovations in the history of metallography and metallurgical study. And the attempts to characterize woods by scientists of the caliber of Michael Faraday spurred many developments in 19th century metallurgy and contributed to the Industrial Revolution. Michael Faraday was the son of a blacksmith and perhaps the greatest experimenter of all times, who tried to duplicate wood steel by alloying iron with a variety of metallic additions, including noble metals, but failed. However, his efforts gave rise to the beginning of the making of modern alloy steels, and which paved the way for the Industrial Revolution. Although the Indian subcontinent has made so many notable contributions which have influenced the Industrial Revolution, as we've pointed out in the case of wood steel and zinc production, it is also very sad that in India, several of the traditional practices of metallurgy have been waning steadily, with the communities facing increasing marginalization. Traditional practices of iron smelting have been nurtured amongst some of the remote communities in the forests, including the tribals such as the Agarias and Asurs in central India, and others in areas such as Jharkhand, Chhattisgarh, and Maharashtra. We have on the one hand the accounts of the Romans who talked about this steel from the Seres, which may be linked to the Chera kingdom of Tamil Nadu and southern India, pointing to the hoary antiquity in the making of high-grade steel and metallurgical products, which were important items of export. However, in the present day, many of these traditions are steadily in decline, and we also need to try to look into how we could preserve and revive these for posterity. In summary, we have gone through the trajectory of the use of numerous metals and alloys in antiquity, going from those which could be used in the native state to those which could be extracted more easily, and finally those which became increasingly more complex in terms of metallurgical processes for production and extraction, such as zinc and steel, almost going to the pre-industrial technologies. And in all of these, we find that the Indian subcontinent also made very notable contributions with some very distinctive and skilled alloys such as the Highton bronzes. And it has been home to several practices of traditional mining, metallurgy and metal processing, although we have to take note of the fact that several of the traditional skills are rapidly declining, with artisans facing increasing marginalization in an era of industrialization and globalization. In the further notes, one can read more about the other types of metals and alloys which were used, such as lead and mercury, and it is quite extraordinary, of course, in the present day. It's been an exponential growth in terms of use of modern metals and materials. But it is these humble attempts to extract and use some of these early metals which laid the foundation of so much of the rise of the great exponential growth in modern material science. Thank you.